Imagine standing at the edge of the universe, looking out into the vast, uncharted expanse. Beyond the farthest stars and galaxies lies a boundary, a point where the observable universe ends and the unknown begins. For centuries, astronomers have gazed deeper into the cosmos, uncovering more and more about the universe's vastness. Yet beyond this edge, there is an entire realm of mysteries. What if there's more to the universe than we could ever see? What if the edge is a doorway to something entirely different? In this journey, we'll explore some fascinating ideas, from alternate dimensions to parallel universes, from cosmic anomalies to the possibility of higher beings watching over us from the fringes of the cosmos. So what lies at the edge? Let's find out.
The boundaries of our vision, what lies at the edge of the observable universe.
Despite the vastness we see when we look up at the night sky, the universe is not endless in terms of what we can observe. There is a boundary to our vision, a limit beyond which we cannot peer, no matter how powerful our telescopes become. This boundary is known as the edge of the observable universe. The observable universe refers to the part of space that we can see and measure with our current technology. It is not a fixed, unchanging boundary, but rather one that is determined by the finite speed of light and the ongoing expansion of the universe.
Light travels incredibly fast, about 300,000 kilometers or 186,000 millimeters. However, even at that speed, it takes time for light to travel across the vast distances of space. When we look at a star in the sky, we're not seeing it as it is right now, but rather as it was when the light left it. In some cases, that could have been millions or even billions of years ago. This means that the farther away an object is, the older the light we see from it, and the further back in time we're looking.
The observable universe is often thought of as a bubble surrounding us. This bubble has a radius of about 46 billion light-years, which is a staggering distance. A light-year is the distance light travels in 1 year, around 9.46 trillion kilometers, or 5.88 trillion miles. So when we say the observable universe is 46 billion light-years in every direction, we're talking about an area of space so vast that it's almost impossible for our human minds to comprehend. Yet, this is just the limit of what we can observe.
Beyond that boundary, there are parts of the universe that remain hidden from us, not because they are obscured by something like dust or gas, but because the light from them has not had enough time to reach us. But even that boundary is not as straightforward as it might seem. The universe has been expanding since the Big Bang, and it continues to expand today. This expansion stretches space itself, meaning that the distance between objects in the universe is increasing over time. As a result, some parts of the universe that were once within our reach are now beyond our observational ability. The light emitted by these distant objects is stretched and redshifted as it travels toward us, shifting it to wavelength we can no longer detect. In a sense, these distant parts of the universe are receding from us faster than light can travel, making it impossible for us to see them no matter how long we wait.
It's easy to think of this boundary as a wall, but in reality, the edge of the observable universe is more like a foggy horizon, constantly shifting and moving outward as our technology improves and as the universe itself continues to evolve. With each new discovery, astronomers are able to peer further into space, uncovering galaxies, stars, and cosmic phenomena that were previously out of sight. And yet, no matter how far we reach, there will always be a limit, a point beyond which we cannot go.
However, just because something lies beyond our observational reach doesn't mean it doesn't exist. There may be countless galaxies, stars, and other cosmic objects beyond the observable universe, but because their light hasn't yet reached us, we have no way of knowing they're there. This presents one of the most intriguing mysteries in cosmology. What lies beyond the observable universe, and how do we know if it even exists? The answer to that question is largely speculative at this point. Some scientists believe that the universe is infinite, extending far beyond what we can see. Others suggest that the universe may be much larger than the observable part, but still finite. These ideas come with their own challenges. For example, if the universe is infinite, then there could be an infinite number of stars, galaxies, and other cosmic structures stretching out forever. On the other hand, if the universe is finite, then it would have some kind of edge or boundary, something that we might never be able to observe, even in theory.
One of the most fascinating aspects of the edge of the observable universe is the idea that as we look further into space, we're also looking further back in time. The light we see from distant galaxies tells us not only about their current state, but also about their past. By studying the oldest light in the universe, known as the cosmic microwave background radiation, or CMB, scientists can learn about the very early stages of the universe, just moments after the Big Bang. This light has traveled through space for over 13 billion years, and by studying it we gain insights into how the universe evolved and what it looked like when it was much younger.
New telescopes, such as the James Webb Space Telescope, or JWST, are already providing us with unprecedented views of distant galaxies, stars, and nebulae. JWST is designed to detect infrared light, which can travel through dust and gas that may block visible light. These advancements have allowed us to see deeper into space and farther back in time than ever before. But even with these advancements, the edge of the observable universe remains a reminder of the limits of our knowledge.
How the cosmic horizon came to be. A history of the universe's edge.
For most of history, humanity had no real understanding of the true scale of the cosmos. Ancient civilizations viewed the stars as a set of twinkling lights in the night sky, often linked to mythology, gods, and storytelling. It wasn't until much later, with the rise of scientific inquiry and tools like telescopes, that our understanding of the universe expanded, and with it, the idea of its boundaries.
One of the most significant breakthroughs came with the work of Albert Einstein and his theory of general relativity. In 1915, Einstein proposed that gravity was not a force acting through space, as Isaac Newton had described, but rather the warping of space itself by mass and energy. This theory reshaped our understanding of space-time, providing the foundation for modern cosmology. Einstein's equations implied that the universe could be dynamic, not just static, and this idea was taken up by others, including the Russian physicist Alexander Friedmann.
Friedmann's work showed that if space could expand, then the universe could change over time. This was a critical step forward, as it suggested that the universe we observe is not fixed in place, but instead a constantly evolving entity. However, it wasn't until the 1920s, with the work of Edwin Hubble, that we would get the first real evidence of an expanding universe.
Hubble's observations of distant galaxies showed that they were moving away from us. The farther a galaxy was, the faster it seemed to be receding. This discovery laid the groundwork for what would later become known as Hubble's law, which states that galaxies move away from us in proportion to their distance. This discovery confirmed that the universe was expanding, providing the first real evidence that space itself was stretching.
In the context of an expanding universe, the concept of the cosmic horizon became a natural consequence. As space itself expanded, the distance between galaxies increased in the early universe. This expansion happened at a rapid pace during an event known as cosmic inflation. This brief period, occurring in the first fraction of a second after the Big Bang, saw the universe expand exponentially. As a result, regions of space that were once in close proximity were suddenly pushed vast distances apart.
The farther an object was, the faster it receded from us. And this recession became a key factor in determining the limits of what we could observe. This relationship between distance and time is critical to understanding the observable universe. If a galaxy is 10 million light-years away, the light we see today left that galaxy 10 million years ago. Because of the vast distances involved, this means that looking at the farthest objects in the universe takes us back to earlier moments in the history of the cosmos. The key insight came when scientists realized that there was a limit to how far we could look due to the finite age of the universe itself. The universe is approximately 13.8 billion years old. This means that the farthest light we can observe comes from objects whose light has been traveling for about 13.8 billion years. This created the first real definition of the observable universe. At the current age of the universe, that distance is roughly 46 billion light-years. The concept of the cosmic horizon was formalized in the mid-20th century with advances in both observational astronomy and theoretical physics. The development of tools like radio telescopes, which could detect longer wavelengths of radiation, and later space telescopes, which could observe the universe in far greater detail than ever before, helped scientists refine their understanding of the universe's limits. These advancements allowed astronomers to study the most distant objects ever observed, including quasars and galaxies billions of light-years away. Each new discovery pushed the boundaries of our observable universe, expanding our understanding of the cosmos.
At the same time, theoretical physicists were refining their models of the universe's structure and evolution. The work of scientists like Albert Einstein, Georges Lemaitre, and Alan Guth contributed to our understanding of cosmic inflation, which helped explain the rapid expansion of the early universe. This theory, developed in the 1980s, proposed that during the first fractions of a second after the Big Bang, the universe expanded exponentially, stretching from subatomic sizes to vast distances. This brief but intense period of expansion set the stage for the structure of the universe as we see it today, and provided a framework for understanding the limits of the observable universe.
The next step in understanding the edge of the observable universe came with the discovery of the CMB. In the 1960s, Penzias and Wilson accidentally discovered the CMB, and it quickly became clear that this radiation held crucial information about the early universe. The study of the CMB allowed scientists to better estimate the size, shape, and age of the universe, which in turn helped to define the boundaries of the observable universe more accurately. Through missions like the Wilkinson Microwave Anisotropy Probe, or WMA, and the Planck satellite, scientists have mapped the CMB with remarkable precision. These maps have revealed subtle variations in the temperature of the radiation, which provide important clues about the distribution of matter and energy in the early universe. By studying the CMB, astronomers have gained insights into the structure and composition of the universe, including the mysterious dark matter and dark energy that seem to make up most of its content. These discoveries have helped to refine our understanding of the universe's age, size, and the limits of what we can observe. The expanding universe. How far can we see? The speed of light, as we know, is a universal constant. Nothing can travel faster than light, right? But here's the tricky part. The expansion of space itself can cause objects to move away from each other at speeds greater than that of light. This doesn't violate the laws of physics, because the expansion is not a movement of galaxies through space, but rather the stretching of space itself. When we say that a distant galaxy is receding from us faster than the speed of light, what we mean is that the space between us and that galaxy is expanding so rapidly that the galaxy is being carried away beyond the reach of light. As galaxies move farther away from us, the light they emit becomes increasingly redshifted, meaning the wavelengths of that light stretch out
shifting it toward the red end of the spectrum. For galaxies far enough away, this redshift becomes so extreme that the light from these galaxies shifts beyond the optical and even infrared spectrum, making them essentially invisible to us.
This is particularly relevant when we look at the most distant galaxies.
As light from these galaxies travels toward us, the expansion of the universe stretches the light so much that it becomes harder to detect.
This process, known as cosmological redshift, is one of the key tools astronomers use to measure the distance to faraway galaxies.
By observing how much the light from these galaxies has been redshifted, scientists can estimate how far away they are and how fast they are moving away from us. The farther a galaxy is, the more its light is redshifted and the harder it becomes to observe. This makes studying the most distant galaxies a challenging task, as their light is stretched beyond the limits of our detection. With the universe's continued expansion, new regions of space are being created. This ongoing expansion means that objects are not only moving away from us, but they are also moving away from each other. The rate of this expansion is not constant, though.
Observations in the late 1990s revealed that the expansion of the universe is actually speeding up. This was a surprising discovery, and it led to the realization that a mysterious force, dubbed dark energy, is driving the acceleration of the universe's expansion.
While dark energy, which makes up about 70% of the universe, is thought to be responsible, we still don't know exactly what it is. As dark energy continues to drive the accelerated expansion, the cosmic horizon will continue to recede, meaning that more and more of the universe will slip beyond our ability to observe it. The more we learn about the universe, the more we realize how little we can actually observe.
Light years and cosmic distances, measuring the unmeasurable.
One light year may seem like a manageable distance, but it's only when you start dealing with hundreds, thousands, or even millions of light years that the true scale becomes apparent.
For instance, the closest star to Earth, Proxima Centauri, is just over 4 light years away.
The Andromeda Galaxy, our nearest galactic neighbor, is about 2.5 million light-years away.
And some of the most distant galaxies we can observe are located billions of light years away.
Each step further into the universe brings the realization that the distances we are working with are so vast that they stretch beyond the limits of human comprehension.
Astronomers have developed several methods to estimate these enormous distances, each of which comes with its own set of strengths and limitations.
One of the most basic methods used is called parallax, which involves observing an object from 2 different viewpoints. Parallax works much like how we can perceive the position of an object to shift when we view it from different angles, such as when you hold your finger up to your eyes and move your head from side to side.
In astronomy, this method is used to measure the distances to nearby stars by observing their position relative to more distant background stars. By measuring the angle of this shift, astronomers can use trigonometry to calculate the star's distance. However, parallax only works for relatively nearby stars, since the shift in position becomes too small to detect over larger distances. For stars or galaxies that are too far away for parallax to be useful, astronomers must rely on other methods to estimate their distances. One of these methods is called standard candles, a technique that uses objects of known brightness, like certain types of stars, to estimate distances. The idea is that if you know how bright an object truly is, aka its intrinsic brightness, and you can measure how bright it appears from Earth, aka its apparent brightness, you can calculate its distance using the inverse square law. This law states that the brightness of an object decreases with the square of the distance from it.
One of the most commonly used standard candles is a type of star known as Cepheid variable stars.
These stars pulse regularly, and the period of their pulsations is related to their intrinsic brightness.
By measuring the period of a Cepheid variable's pulsations, astronomers can determine its true brightness. By comparing this to how bright it appears from Earth, they can estimate its distance.
Cepheid variables are useful for measuring distances within our own galaxy and to nearby galaxies.
But for more distant objects, astronomers have to rely on even more powerful methods. As the distances involved become greater, astronomers start using redshift to measure the expansion of the universe. By measuring the amount of redshift, astronomers can calculate how fast a galaxy is moving away from us, and from that, they can estimate its distance. Redshift is particularly useful for measuring the distances to extremely distant galaxies, including those at the very edge of the observable universe. By measuring the redshift of a galaxy, astronomers can use Hubble's law to determine how far away it is. This method has been instrumental in our understanding of the large-scale structure of the universe and has helped to reveal the vastness of the cosmos. While parallax, standard candles and redshift are the primary methods used to measure distances in the universe, there are also other more specialized techniques used for certain types of objects. For example, in some cases, astronomers can use gravitational lensing to estimate distances. Gravitational lensing occurs when a massive object, like a galaxy or cluster of galaxies, bends and magnifies the light from objects behind it. By studying the way light is bent, astronomers can estimate the distance to the lensing object. Similarly, astronomers can use the CMB to measure the overall size of the universe and help refine distance estimates for faraway objects. Despite these sophisticated methods, there are still many challenges in measuring cosmic distances accurately. One of the main difficulties is that the further away an object is, the more complicated the calculations become. Each method of distance measurement relies on certain assumptions, and as the distances get larger, these assumptions can introduce more uncertainty into the results. For example, the standard candle method relies on knowing the intrinsic brightness of an object. But if that object's properties change or are different from what we expect, the distance estimate can be off. Similarly, redshift measurements are based on the assumption that galaxies are moving away from us due to the expansion of space. But there are other factors, like gravitational interactions, that can also cause galaxies to shift in their positions. Furthermore, there are also challenges related to the precision of the tools we use to measure cosmic distances. Telescopes and detectors are limited by the amount of light they can collect and the precision with which they can measure wavelengths of light. As we look farther and farther into space, the light from distant objects becomes dimmer and the wavelengths of light become stretched, making it harder to detect and measure accurately. This is especially true for the most distant galaxies, where the light we see has been traveling for billions of years and is extremely faint. Despite these challenges, astronomers have made incredible progress in measuring the distances to faraway objects in the universe. The methods we have today allow us to estimate distances to galaxies billions of light years away with remarkable precision. However, the vastness of the universe means that there is still much we don't know about the true scale of the cosmos. As our tools improve and our understanding of the universe deepens, it's likely that we will be able to measure distances even more precisely and discover new methods of peering into the farthest reaches of space. By accurately determining distances, we can begin to comprehend how the universe has evolved, how its structure has formed, and how it will continue to expand into the future. No one knows exactly what dark energy is. One idea is that it's related to the energy of empty space. Even in a perfect vacuum, space with no particles, no light, nothing at all, there might still be energy present. This energy wouldn't clump or spread like matter. Instead, it would remain constant as space grows. In fact, the more space there is, the more of this energy there would be. So, as the universe expands, dark energy becomes more and more dominant.
Another idea comes from a theory Albert Einstein once proposed. Before the Big Bang theory was known, Einstein believed the universe should be static, not growing or shrinking. To make this work, he added a term to his equations called the cosmological constant. It was meant to balance gravity and keep the universe stable. Later, when astronomers discovered that the universe was expanding, Einstein dropped the idea and called it his biggest blunder. But after the discovery of accelerated expansion, the cosmological constant made a comeback. It seemed to describe exactly the kind of force dark energy might be.
Whether it's a cosmological constant or something even stranger, the effects of dark energy are clear. It's the dominant force in the universe today. Matter, including stars, galaxies, and everything we can see, makes up only about 5% of the total energy content of the cosmos. Dark matter, another invisible substance that holds galaxies together with its gravity, adds about 27%. The rest is dark energy. It's not just a part of the universe, it's the biggest part. In billions of years, even the closest galaxies may slip beyond our reach. The night sky will become emptier. Future astronomers may look up and see only a few nearby stars, unaware of the grand universe that once filled the sky.
Scientists are trying to learn more about dark energy using different methods. Some are looking at supernova, just like the original teams did. Others are studying the structure of the universe, how galaxies are arranged across space, and how they've changed over time. Still others are using powerful telescopes to look for tiny effects of dark energy on light coming from distant galaxies. There are even plans for new space missions dedicated to dark energy. One of these is the Euclid mission, launched by the European Space Agency. Another is NASA's Roman Space Telescope, which will search for answers about how dark energy has shaped the universe over billions of years. These missions will gather more detailed data than ever before, using modern instruments that can detect changes across enormous scales.
There's also hope that experiments on Earth might help.
Some physicists believe that dark energy might be connected to other areas of physics, like quantum mechanics or gravity. There might even be particles or fields we haven't discovered yet, ones that help explain the behavior of dark energy. If that's true, it could open up an entirely new view of the universe. One that connects the smallest building blocks of matter with the largest structures in space. Whether it continues to expand forever, tears itself apart, or finds some unexpected balance, will depend on this invisible force that fills the fabric of space itself. We are still at the beginning of understanding it, but every discovery brings us closer to grasping the full scale of our universe and how it keeps changing around us.
Chasing the farthermost galaxies. The frontier of cosmic exploration. At the far edge of the observable universe lie the most distant galaxies ever discovered. But finding and studying these distant objects is one of the hardest things in astronomy. The Hubble Space Telescope, launched in 1990, changed everything. Floating above Earth's atmosphere, Hubble had a clear, steady view of the universe. Over time, astronomers began pointing it toward dark patches of sky. Places where no stars, no galaxies, nothing seemed to be. The goal was simple: stare into the darkness for as long as possible and see what might appear. What came out of these long exposures were images packed with galaxies. Some were nearby, others were extremely far away. One of the most famous images from this project is called the Hubble Ultra Deep Field. It shows a tiny region of sky about the size of a grain of sand held at arm's length, but it's filled with thousands of galaxies. Galaxies from the universe's early days are usually small, faint, and oddly shaped. Some look like clumps. Others are stretched or broken apart. They haven't had time to settle into the neat spiral or elliptical shapes we see in modern galaxies like our Milky Way. Finding these early galaxies is not easy. Their light is redshifted as it travels through space. They no longer glow in the colors our eyes can see. Hubble was equipped with infrared sensors that made this kind of observation possible, but there were still limits. Some galaxies were so far away and so faint that even Hubble couldn't see them clearly.
That's one reason astronomers were excited for the launch of the JWST. Launched in 2021, JWST was designed to see in infrared. It could pick up the faint heat signatures of ancient galaxies with more sensitivity than any telescope before it. Within its first year, Webb delivered groundbreaking discoveries. It found several galaxies that appeared to be even older and farther than expected. Some of them may have formed just 300 million years after the Big Bang. That's incredibly early, considering that the first stars likely didn't form until around 100 to 200 million years after the universe began.
How could galaxies form so fast? How could they grow so large, so soon? The answers are still being debated. Some astronomers think we may need to adjust our models of galaxy formation. Others suggest that we might be seeing something new or unexpected. Perhaps early black holes helping galaxies grow quickly by pulling matter in and causing stars to form faster.
Still, observing these far-off galaxies takes a lot of work. First, astronomers need to know where to look. This usually starts with a wide area survey, an image of a big part of the sky. They scan it for faint smudges that don't look like nearby stars or galaxies. Then, they take closer looks using powerful instruments. They measure the redshift of the light to estimate how far away the object is. But redshift measurements can be tricky. Sometimes other factors can mimic the effects of high redshift. Dust clouds, nearby stars, or even the structure of the galaxy itself can cause confusion. That's why astronomers often use multiple methods to confirm a galaxy's distance. They compare data from different telescopes, check for specific patterns in the light, and look at the galaxy's shape and brightness.
At such distances, we're seeing these galaxies not as they are now, but as they were when the universe was still forming. They may be completely different today, merged with others, pulled apart, or changed by cosmic events. Sometimes, nature lends a helping hand. Gravitational lensing from massive galaxy clusters can act like giant magnifying glasses. These clusters bend the light from galaxies behind them, making the distant galaxies appear larger and brighter. In some cases, lensing has helped astronomers spot galaxies that existed only a few 100 million years after the Big Bang.
With JWST and future telescopes like the Roman Space Telescope, astronomers hope to find even more ancient galaxies, perhaps ones from just 200 million years after the Big Bang or earlier. Each new galaxy discovered at these distances pushes the boundary of our vision just a little further, and each one helps answer the same question: how did we get from a universe of hydrogen and helium gas to a universe filled with stars, galaxies, and eventually, every dot on a telescope's image might be a clue. Every blurry smudge could be the key to understanding how the universe took shape. And somewhere out there, just beyond the edge of what we can see, may be galaxies whose light will never arrive, but whose story is already part of the grand tale of everything.
One of the oldest galaxies ever observed, GNZ 11, is a small, faint galaxy that has made a big impact in the world of astronomy. When scientists discovered it, they realized they might be looking at the oldest galaxy ever captured by a telescope. It was first discovered using data from the Hubble Space Telescope. Researchers were studying a part of the sky using deep imaging techniques, hoping to spot galaxies from the very beginning of cosmic history. GNZ 11 stood out from the crowd. It was tiny, faint, and glowing in infrared light. Just the kind of signal astronomers expect from something very far away.
When scientists studied its light more closely, they found that GNZ 11 had a redshift of about 10. Its light began traveling to us just 400 million years after the Big Bang. That might sound like a lot, but in cosmic time, it's just the blink of an eye. It means this galaxy existed when the universe was only about 3% of its current age. Most of the stars, galaxies, and clusters we know today had not yet formed. The cosmos was still going through its early growing pains.
One of the most surprising things about GNZ 11 is how developed it seems to be, despite its age. You might expect a galaxy this old to be small and chaotic, full of gas and dust, but not many stars. But GNZ 11 already shows signs of having active star formation. Scientists believe it was producing stars at a much faster rate than most galaxies do today. In a time when the universe was still dark and unformed, GNZ 11 was already hard at work building light and structure.
What allowed GNZ 11 to grow and start producing stars in such a short time? Astronomers are still trying to answer this question. Some believe that the earliest galaxies might have formed faster than we expected because of high-density regions of matter in the early universe.
At the time of its discovery, GNZ 11 was considered the record holder. No other confirmed galaxy had ever been seen at a higher redshift. But even as scientists studied it, new tools were already being prepared that could look even farther. Not long after JWST began sending back data, hints of galaxies even farther away than GNZ 11 started to emerge. Some of these new discoveries, like JADE's GSZ 13-0, appeared to come from galaxies that existed just 300 million years after the Big Bang. But even as these newer findings make headlines, GNZ 11 remains one of the most studied examples of an early galaxy. Its discovery marked a turning point in how far we could see and how far back in time we could look.
Studying such a distant object isn't easy. It took a lot of careful data collection and analysis to confirm its distance. At first, researchers used what's called photometric redshift. This method estimates how far away something is by comparing the brightness of its light in different filters. But photometric redshift isn't always precise. To be sure of GNZ 11's distance, scientists later used a more direct method, spectroscopic redshift. In this method, they broke down the galaxy's light into its component colors and looked for specific patterns or lines that show where certain elements absorb or emit light. These lines are like fingerprints. When they appear shifted to the red end of the spectrum, scientists can calculate exactly how much the universe has stretched since the light left the galaxy. This gave them a much more accurate picture of GNZ 11's distance and age.
Even though GNZ 11 is billions of light years away, its light still tells us so much. By studying its spectrum, astronomers can figure out what elements it contains, how fast it's forming stars, and even get clues about whether early black holes might be growing inside. That kind of information helps fill in the blanks in our understanding of the universe's first billion years, a period sometimes called the cosmic dawn. The journey of that light starting so long ago and traveling across space to finally reach Earth is a reminder of how large the universe is and how small we are in it. But it also shows how far human curiosity can reach. From a telescope floating high above our planet, scientists were able to catch a glimpse of something that no human being could ever visit. Something that happened billions of years before our solar system existed.
GNZ-11 may not have held the record forever, but it opened the door to a new era of discovery. It showed that we could push beyond what was once thought to be the limit. It reminded us that the edge of the observable universe is not a wall, but a frontier. A place where each new discovery brings more questions, more wonder, and more clues to the origin of everything.
The impact of the Hubble Deep Field on our understanding of the universe's edge. Before the Hubble Deep Field image was taken, no one was completely sure what to expect. There were debates about whether it was worth pointing a billion-dollar telescope at what seemed to be nothing. But astronomers were curious. They wanted to see just how deep they could look into space if they gave the telescope enough time to collect light. They knew that light from the farthest objects takes billions of years to reach us. So, by focusing on a seemingly empty part of the sky, they hoped to see galaxies from the early universe. When the final image was processed, what appeared was a sea of galaxies. Not just a few, thousands of them. Each little smudge, dot, and swirl in the image was a galaxy, some with hundreds of billions of stars. These galaxies were spread across different stages of time and distance. Some were nearby, but many were billions of light years away. This was the first time humanity had seen such a deep look into space. It wasn't just a pretty picture, it was proof that the universe was full of galaxies in every direction, even in places where the sky looks completely black to our eyes.
Before this, we had no real idea of just how filled with structure the distant universe was. The Hubble Deep Field revealed that galaxies were not only more numerous than we thought, but that they came in all shapes, sizes, and stages of development. It was a record of cosmic history written in light. What made the image so powerful was that it wasn't aimed at a special or known region of space. It was picked specifically because it was unremarkable. No nearby stars, no visible galaxies, nothing bright or interesting. That meant the results weren't biased. The image could be seen as a fair sample of what the universe looks like in general. If that tiny patch of sky held thousands of galaxies, it meant the entire universe must hold hundreds of billions of them, or maybe even more.
Suddenly, our view of the universe's scale exploded. The galaxies in the deep field also help scientists understand how galaxies evolve over time. Some in the image look smooth and round, like mature elliptical galaxies. Others look chaotic and clumpy, showing signs of active star formation and early growth. By comparing these far-off galaxies to those nearby, astronomers could trace how galaxies changed over billions of years. It was like flipping through a photo album of the universe, with snapshots from different ages showing how galaxies began, collided, and settled into the structures we see today. The data from the deep field helped refine estimates of the universe's age. By counting galaxies at different distances and comparing their properties, scientists could better model the timeline of cosmic expansion. They could test theories about how quickly stars and galaxies formed, how matter clumped together under gravity, and how energy spread out over time. It became one of the key tools for understanding cosmology.
The success of the original Hubble Deep Field led to more versions. There was the Hubble Ultra Deep Field, which went even deeper by collecting light over 11 days. Later came the Extreme Deep Field, combining over 10 years of data into one image that included galaxies dating back over 13 billion years. Each time astronomers managed to squeeze out just a little more light from the universe's early days. And each time the story grew richer. These images sparked imagination. They became iconic. People who had never studied astronomy before looked at them and felt a sense of awe. It was like standing on a shoreline, looking out over an ocean you never knew existed, stretching beyond what you can see or measure.
Behind the scenes, making these images wasn't simple. The Hubble telescope had to be kept incredibly steady, locked in position to gather faint signals from deep space. Engineers and scientists had to process the raw data carefully, cleaning up the noise and combining exposures to create the final image. It took skill, patience, and a belief that looking into the darkness would be worth it, and it was.
The Hubble Deep Field proved that even the quietest part of the sky was full of life, structure, and history. It gave astronomers a better sense of where we are in the universe, not in a special place, not near the center, just in a galaxy among billions, part of a cosmos that stretches beyond our collective imaginations. It showed that the edge of our vision is always moving. With better tools, sharper eyes, and longer observations, we continue to chase it further, revealing new galaxies, new mysteries, and new light that has waited billions of years to be seen.
Thanks to this image and the ones that followed, we now know that even the darkest part of the sky is alive with distant galaxies. It reminded us that the universe is bigger, older, and more filled with wonders than we had ever imagined, and that we've only just begun to see what lies out there. The evolution of cosmic structures from first stars to superclusters. Right after the Big Bang, the universe was hot and dense. Particles moved so fast they couldn't form atoms. But as the universe expanded, it also cooled. Eventually, temperatures dropped enough for electrons and protons to join and form hydrogen atoms. But while the universe became transparent, it was still dark. There were no stars yet, just clouds of gas floating in a cold and growing universe.
Within these clouds, there were tiny differences in density. Some areas were just a little thicker than others, but that was enough. Gravity started to pull the denser areas together. Over millions of years, these small lumps of gas collapsed further. As the pressure and temperature rose, the first stars were born.
These stars were different from the ones we see now. They were massive, hot, and short-lived. They burned bright and died young, often exploding in powerful supernovae. But they were the universe's first light, turning the cosmic darkness into the beginnings of the starlit sky.
These first stars also helped create new elements. At the beginning, the universe had mostly hydrogen and a little helium. Heavier elements like carbon, oxygen, and iron didn't exist yet. But inside the first stars, nuclear reactions created these elements. When the stars exploded, they spread this material out into space, enriching the gas and making it possible for new generations of stars and planets to form.
This process of stars forming, dying, and spreading their contents became the engine behind cosmic growth. Stars didn't form alone. They gathered into groups, what we now call galaxies. Some of the earliest galaxies were small, just a few million stars. But as time went on, galaxies began to merge. Gravity pulled them into larger and more complex shapes. These mergers weren't peaceful. They triggered waves of star formation, collisions, and the growth of giant black holes in their centers. Still, this was how larger galaxies formed, step by step, over billions of years, through the joining of smaller ones.
Even galaxies didn't stay isolated. They were drawn together by gravity, forming groups and clusters. These clusters could hold hundreds or even thousands of galaxies. Between them was hot gas, dark matter, and the remnants of past galactic encounters.
But the growth didn't stop there. Clusters came together to form superclusters, vast web-like structures stretching across hundreds of millions of light-years. These superclusters form what we call the cosmic web, a pattern of filaments and nodes where matter is concentrated, separated by huge voids of empty space. This giant web of matter is not random. It traces the original patterns found in the CMB. Those early tiny differences in density grew over time into the giant features we see today. Gravity acted like a sculptor, turning faint ripples into mountains of galaxies.
Computer simulations have played a big role in helping us understand this evolution. Scientists use the laws of physics to model how matter behaves in the universe. They start with conditions based on the early universe and let gravity, gas pressure, radiation, and other forces play out over billions of years. What they get are virtual universes that look surprisingly similar to our own. These models show galaxies forming along the threads of the cosmic web, falling into clusters and merging over time. They give us a picture of the universe's history that matches what we see through our telescopes.
One important piece of this puzzle is dark matter. We can't see it, but we know it's there. It makes up most of the matter in the universe, and it doesn't give off light or interact with normal matter in ways we can easily detect. But it does have gravity, and that makes all the difference. Dark matter formed the original scaffolding for structure. Galaxies and clusters grew around these invisible clumps, guided by their pull. Without dark matter, the universe would look very different, more spread out, less connected, maybe even lifeless.
As the universe aged, stars kept forming, but more slowly, galaxies began to settle into calmer shapes. Elliptical galaxies formed from mergers, while spiral galaxies like our Milky Way kept forming stars in their swirling arms. Inside these galaxies, new stars were born from clouds of gas, while older stars aged and dimmed. Some galaxies stopped forming stars altogether, becoming red and quiet. Others continued to grow by pulling in gas or swallowing smaller neighbors. Clusters too evolved. The space between galaxies in a cluster is not empty. It's filled with hot gas, dark matter, and sometimes giant shock waves from past collisions. Telescopes that detect X-rays have shown us the glow of this hot gas, revealing how clusters are connected and how they've changed. In the largest clusters, galaxies move at high speeds, pulled by the combined gravity of all the matter inside. These clusters are some of the most massive structures in the universe, and they're still growing. Superclusters are harder to define. They don't have clear edges or centers. Instead, they're part of the larger cosmic web.
Our own Milky Way belongs to the local group, a small cluster of galaxies. That group is part of the Virgo supercluster, which itself is part of an even bigger structure known as Laniakea. These names help us understand where we are in the grand scheme of things, but they're just labels for regions of a much larger, interconnected universe.
The structure of the universe is always changing. Galaxies collide, stars are born and die, clusters grow larger, but the pattern, the web, remains. It's a result of how the universe began, how gravity shaped it, and how matter moved through time. When we look out at the sky, we're seeing the result of billions of years of growth, shaped by forces both seen and unseen. Even now, the story continues to unfold, with new discoveries helping us trace the threads of the cosmos ever deeper into time and space. The mysterious void. Why does empty space exist between galaxies? If you could zoom far out from Earth, past the solar system, beyond the Milky Way, and even past the nearest groups of galaxies, you would eventually see something surprising. The universe, when viewed on its largest scales, is not evenly filled with galaxies. Instead, it looks like a sponge or a web. There are bright strands made up of galaxies and clusters. all connected like a giant network. But between those strands are huge dark areas. These are the cosmic voids, vast regions where almost nothing exists. They can stretch for hundreds of millions of light years, and in some cases may contain just a few galaxies or none at all. As matter was pulled into denser areas, it left behind regions with less and less material. These became the voids. As the universe kept expanding, these underdense areas grew larger, not because they were gaining mass, but because the surrounding regions were pulling matter away from them. In a sense, the voids are like the spaces between the threads of the cosmic web. They're not totally empty, but they're much less crowded than the areas where galaxies gather.
Scientists started noticing these voids as they mapped the positions of galaxies. Surveys of the sky in the 20th century revealed patterns in how galaxies are distributed. Instead of being scattered randomly, they appeared to line up in chains and walls, with large gaps in between.
One of the earliest signs of this came from the CFA redshift survey in the 1980s. It showed that galaxies formed patterns with giant holes, some over 100 million light-years across. As more powerful telescopes and better sky surveys became available, the picture grew clearer. The universe really did have these enormous empty spaces, and they were not rare.
One of the most famous voids is the Brutus Void. It was discovered in 1981 and is often called the Great Nothing. It spans over 300 million light-years across. Inside it, a handful of galaxies have been found. There are hundreds, maybe thousands, of such voids scattered across the universe. Together, they fill most of space. Even though galaxies and clusters make up the parts we can see, voids actually take up most of the volume of the cosmos.
Voids have structure, just like the rest of the universe. Some voids are completely isolated, while others are linked by thin strands of galaxies. Some may have small groups of galaxies inside them, orbiting each other quietly.
The galaxies in voids tend to look different from those in crowded areas.
They often have more gas, fewer stars, and less dust.
Some astronomers think these galaxies are slower to evolve because they're not influenced by the gravity of nearby galaxies or the effects of collisions. They live in peace, far from the busy neighborhoods of the cosmic web.
Understanding voids helps scientists test theories about how the universe works. For example, because voids grow over time, they're sensitive to the effects of dark energy. By measuring the size and shape of voids, researchers can learn how fast the universe is expanding. Voids also help us study gravity on large scales. If gravity worked differently than we thought, voids might look different too. Some researchers use computer simulations to compare real voids with ones generated by different models of the universe. So far, the patterns we see in the sky match the models pretty well, but there's still a lot to learn.
The formation of voids is a natural part of how the universe organizes itself. Imagine a field full of hills and valleys. The hills represent dense regions where galaxies form. The valleys are the voids. As time goes on, the hills grow taller, pulling matter toward them. The valleys become deeper and emptier as the matter is drawn away.
This is what happens in the universe. The dense areas get denser, and the empty areas get emptier. What's also interesting is how the boundaries of voids, where they meet the denser parts of the universe, can be areas of activity. These regions can act like highways for galaxies, directing their motion along the threads of the cosmic web. Galaxies near the edges of voids might be moving outward, away from the center, as if being pushed. In reality, they're being pulled by gravity from the denser regions nearby, but it gives the impression that the void itself is expanding.
Because voids are less crowded, the effects of dark matter or dark energy
might be easier to detect there. For example, gravitational lensing can be measured even in voids. If you look at how background galaxies are distorted, these tiny effects could offer new clues about what's filling the universe besides visible matter.
There are also unusual voids that don't fit neatly into our current models. Some are larger than expected, others seem too empty. These may be rare statistical events, or they might hint at something deeper. Some researchers have even wondered if we live inside a void, and that the universe looks like it's expanding faster because we're in a low-density area. This idea has mostly been ruled out by other evidence, but it shows how voids are still an active area of study.
Even though they are empty compared to other parts of space, voids are not boring. They are quiet places in a loud universe. They help shape the motion of galaxies. They give us clues about dark energy and cosmic growth.
Right, galaxies light up the cosmic web. But it's the darkness between them that defines the shape of everything. In a way, cosmic voids are like the silence between notes in music. They give form to the whole, allowing the structure of the universe to be seen more clearly. Without them, the cosmos would look completely different, more like a fog. So even the emptiest places in space have a story to tell.
What lies beyond the observable universe? One of the most widely held ideas on what lies outside the invisible boundary is that space is infinite. If the universe has no edge and no center, then what we see is only a tiny part of a much bigger structure. In this view, galaxies keep going far beyond the limits of what we can observe. There could be countless other galaxies, stars, and possibly even planets. If space is infinite, then the universe is filled with matter far beyond the range of our tools.
But infinity is a difficult idea. It's hard to prove or measure. And even if space is infinite, that doesn't mean the universe is the same everywhere. Some scientists think there could be parts of space that look very different from what we see. The laws of physics might not be the same in every region. Some areas might have different values for gravity or different types of particles. These ideas come from theories about how the early universe grew, especially cosmic inflation. But inflation also opens the door to something strange, the idea of a multiverse. In some versions of inflation theory, inflation never ends in some parts of space. Instead, it keeps going, creating new regions of space over and over again. Each of these regions might become a separate universe with its own set of physical rules. In this way, our universe could be just one bubble in a vast multiverse. We would never see these other bubbles because they would lie far beyond our cosmic horizon, separated by space that's still inflating. But the theory suggests they could exist, and that the cosmos is much more complex than it appears.
Other ideas are even more strange. Some physicists think the entire universe we know might be just a slice of a higher dimensional space. In this view, our universe is like a page in a very thick book. Other pages, other universes, could exist side by side with ours, but we wouldn't be able to interact with them. This idea comes from string theory and related models that try to describe all of nature's forces in one framework.
There are also theories that suggest space itself might curve in ways we don't have the tools to detect yet. In this case, the universe could wrap around on itself. If you traveled far enough in one direction, you might come back to your starting point, just like walking around a globe. This kind of shape would mean the universe is finite, but without edges. However, because the scale is so vast, we wouldn't be able to test it easily. While science tries to stay grounded in evidence, imagination also plays a role in thinking about what's beyond the observable universe. Science fiction has long explored these ideas, sometimes stretching them in wild directions. In many stories, other universes contain versions of ourselves, different histories, or completely alien laws of nature. Some stories imagine whole civilizations that exist beyond our cosmic horizon, hidden from view, but perhaps watching us from afar.
While those ideas may seem far-fetched, they raise real questions. Could life evolve in ways we've never imagined? Could there be entire universes where stars never formed? What if there are dimensions we haven't discovered yet, folded into the fabric of space? These questions remind us how little we truly know about the universe.